recording. And we need to turn the projector on. Oh boy. It needs to be Christmas right now. Like, it really does. I just want to hang out on my couch and read my book and drink tea. And, like, just be cozy. Just cozy. This whole driving to school and teaching nonsense for the birds, I tell you. Okay. Number 6. So as I was saying, some people get weirded out by the fact that we have a solid here, but we are adding it to a solution. And what will solid NaCl do when we put it into a solution? It will dissolve, yes? And we will have a reaction because we have a solution of silver nitrate, yes? And we want to know when we will get a precipitate. So, will we get a precipitate if the product of the molar concentration of Ag and Cl is less than Ksp? Will we get a precipitate if that's the case? No. No precipitate will occur unless the solution becomes saturated with NaCl first. Does that make any sense? No, that's just gobbledygoo. Yes, people, they're just making stuff up. The product of the molar concentrations of silver and chloride exceed. You guys know what exceeds mean? Is bigger than. Ksp, will we get a precipitate if that is the case? Yes. So that is our answer. Okay, number 12. Which one of the following relationships is the relationship between the solubility, which I'm going to call X, okay, and the solubility product? What is the solubility product? That is the Ksp. Okay, solubility product is the Ksp. So we have a compound, lead chloride, which is the format AB2, which means we have an ion relationship of 1 to 2. If you know the shortcut, this would be a really good place to use it. Yes? And the shortcut is that for a 1 to 2 compound, Ksp, what is it equal to? 4x cubed. Would anyone like to see how we derive that? Yes? Okay. So if I have lead chloride, PbCl2, Pb2+, and this is going to apply to any compound that's a 1 to 2 or 2 to 1, plus 2Cl minus. And I say let X be the solubility, yes? Then this is going to be X, this is X, and this is 2X, yes? Ksp then is lead 2+ times chloride squared, which then gives us X times 2X all squared, which gives us X times 2 squared is 4, X squared is X squared, and that gives us 4X cubed. So you can derive that if you have forgotten it, but on a multiple choice, and on a written response, you should be writing all of that. But this is multiple choice, so you can just go straight to here if you know this, and you can say, okay, well, if my solubility is X, then I just need to solve for X. So I'm going to take Ksp equals 4x cubed, and I'm going to solve for x. So first of all, I'm going to take Ksp and divide by 4. And then x is going to be the cube root of KSP over 4. And there we are. That's it. This is multiple choice. You just need to circle the correct answer. You don't need to write anything. On a written response, if you just go, like if you're missing this, and let X equal the solubility, and if you're missing your this, then you're out of luck. On the multiple choice, no. Multiple choice is sad that way. You either got it or you don't. Okay? Alrighty. Number 13. Ooh, 13. I would not give you 13 on this test, but after today or tomorrow, I would expect you to know how to do it. Okay? This would be a perfect kind of a question to ask on a midterm or final kind of exam, because it combines this unit with Bronsted-Lowry acid-base theory. Oh! Okay, so here we go. We have silver acetate. This particular question will not be on this test, but the principle behind it will be on the test, just not this specific instance. Okay? We want to know what would cause more AgCH3COO to dissolve, which means we want it to shift to the right. Now, if we add some crystals of AgNO3, of course, that's going to separate into Ag plus and NO3 minus, right, because it'll dissolve. If the concentration of Ag plus goes up, which way will our equilibrium shift? It'll shift left. Is that what we wanted to happen? No. And in fact, the similar thing is going to happen here, because we're going to get CH3COO minus being produced. Therefore, the concentration of CH3COO minus goes up. And again, it's going to shift left. So that's not the answer, and that's not the answer. The evaporation of some water from the solution with no temperature change, well, that makes no sense, because if you're having less solvents, you're certainly not going to dissolve more solutes. Yes? So actually, I could ask this question simply based on process of elimination. However, you're good? Okay. If we add some concentrated nitric acid, what do we get? H plus and NO3 minus. Now, it turns out, and this is what I don't expect you to know just yet, that CH3COO minus is a Bronsted Lowry base. What do Bronsted Lowry bases do? Bronsted Lowry bases are something acceptors. Proton acceptors, yes. And when we say proton in the context of acids and bases, what do we mean? What is a proton? It is a H plus ion, because if you think about it, hydrogen, what is it? It's a proton, a single proton, because its atomic number is 1, and it has a single electron going around the outside. If you take that electron away, what's left? A proton. So a proton is an H+ ion. And in acid and base, we often refer to H+ simply as a proton. So CH3COO- is a proton acceptor. Okay? And what that means is that if you provide it with an H+, which we are doing here, you will have CH3, COO- plus H+, and you will get CH3, COOH. Yes? And because it's an organic acid, we put this hydrogen on the end. Normally, you would put the hydrogen on the front. Okay, but in this one, we'll learn a little bit more about that later, but we put the hydrogen on the end. So, if that's the case, what has happened to our concentration of acetate, CH3COO-? That has gone down, and that means it's going to shift to the right, which is what we wanted. Okay, number 22. So we have 1 mole of Cu2 plus is put into 1 liter of water. And, or sorry, not 1 mole, 1 times 10 to the negative 3 moles. And OH minus is also in 1 liter of water. So in fact, I could just do this and say that's molar OH, yes. And just get rid of that part, and molar Cu2 plus. I would like to know what is true about the trial KSP. Well, CuOH2 dissociates like this. So our KSP expression will be KSP is equal to the concentration of copper times the concentration of hydroxide squared. So I know the concentration of copper. It's 1 times 10 to the minus 3. And I know the concentration of hydroxide. It is 9 times 10 to the minus 3. And then I'm going to square that. And we get 1E3 negative times 9E3 negative squared equals 8.1 times 10 to the negative 8. Is good? Okay. Thank you, that's much nicer. 22, 25. Oh, yeah, that's all we needed, right? Yeah, okay. Didn't want us to compare it or anything. 25. Consider the following. Which of the following will increase the solubility of Ag2CrO4? So which way do we want the equilibrium to shift if we are increasing the solubility? Yeah, we want it to be shifting to the right. So some things that will not cause it to shift to the right is if we increase the concentration of CrO4 to minus. Yes, that would cause it to shift to the left. And you'll notice I'm just ignoring these spectator ions here, like sodium, because I know it's soluble with everything. I can just be like, who's important there? Oh, it's chromate. Who's important in silver acetate? Silver, just silver, because we're dealing with silver here, yes? And so it's the silver that's important, so we have increased the concentration of silver. And so again, that's going to shift left, which is not what we want to happen. What will happen if we add more of this solid here? Nothing, because changing this solid will have no effect on the equilibrium. Solids do not affect the equilibrium. And when I say a solid, I don't mean you add some other solid and it dissolves and then its ion has an effect. I mean the low solubility solid that's on the left, that solid has no effect on the position of the equilibrium. Like solid silver? It would have no effect because it is not silver plus. Oh, that's what we did here. You can't add just that part alone. Ions have to be part of a compound. They don't come on their own, ever. Yes? 29, sure, yeah. Now, let's take a look at Ki, because that's our only one that's left here. And so we could do it again by process of elimination and say these ones don't make it, this one doesn't make it shift, and the others make it shift the wrong way. Why is Ki going to make it shift to the right? We have K plus and we have I minus. Who could have an effect there? Yeah, Ag and I can get together. And then the concentration of silver goes down. Yep. And then that shifts it to the right. Okay, 29. Which of the following solutes could dissolve to produce at least 0.1 molar? Now, what's special about 0.1 molar? Oh, 0.1 molar means that you have a compound that is soluble. Only soluble compounds can produce 0.1 molar or higher. So if we want to produce at least 0.1, we are looking for the soluble compound. Yes? Yeah, you'll look at your data table. Oh, or you might even be able to do it just by knowing some stuff. Na is always soluble, and therefore, boom, there you are. Okay? If you hadn't known that, you might have had to look at, or if they hadn't given you an obvious one, like sodium, like if they gave you, say, calcium sulfate, which I think is soluble? No. Say they gave you strontium hydroxide, or whatever. I don't know. Whatever, anyway, you might have to look it up, but in this case you don't, because we know that all alkalis are soluble. Okay, let's see, we're out of the 20s, and now we're into the 60s, so we are at 63. And the questions at this point, after question 60, they are no longer from old government exams, they're from a different source, and some of them have turned out to be somewhat problematic because they're not like as well edited and stuff, and I just copied them. So we'll find out if any of these are on that list of sort of weird ones. 63. Well, we'll do 67 as well, but 63 comes before 67, so yeah. Okay. What is the concentration of iron and sulfate when we have 25? Ooh, I know what's wrong here. That's not going to be 25 moles. That's a huge quantity. Yes? It's going to be maybe 0.25. Let's try 0.25 in 500. 0.25 divided by 0.5 is, yeah, no, not even that. Yeah, maybe, yeah. So this should be 0.25. So that's the problem there, but let's work with it now. So if we have 0.25 moles in 500 milliliters, or 0.5 liters, that gives us 0.5 molar, and that is Fe2SO4 3. So if that's the case, what is the concentration of Fe? It's going to be 1 because when this dissociates, we end up with 2 Fe's. And so 0.5 would give us 1.0. And then it gives us 3 SO4 2 minuses. And so that would be 3 times as much, which would be 1.5. Yes? Okay, 64. Okay, 64. The following solutes are given. Which of the following will form only molecular aqueous solutions? Okay, so we need something that does not have ions in it. Does NH4-2CO3 have ions? Yeah, it's got ions. It's got NH4+, and it's got CO3 2-. That's the one where it is all made of nonmetals, but because it's got ammonium, it is still an ionic compound. How about this C4H9OH? Is that ionic? No, it's all nonmetals. This is actually an alcohol. Okay, alcohols end in OH. How about lithium acetate? Ionic. And C6H12O6? That is molecular, and that's glucose, actually. So this, or fructose, any monomeric thingy. Monosaccharide, that's what I'm trying to say. And so these two would be molecular. So that would be 2 and 4, because they are all made of nonmetals, but not containing NH4. 67. So we have a saturated solution of iron fluoride, and the concentration of fluoride is 1.68 times 10 to the negative 2. Yes? Now, if you remember when we did solubility, we would say I've got X here, let X be my solubility, and then this will be X and this will be 2X. So what is the solubility? It's going to be 1/2 of 1.68 times 10 to the minus 2. I think the answer for this one, I think there's a problem. I'm just going to do the math here because I don't trust me doing math in my head. But I was right. This should actually be times 10 to the negative 3. Okay, because otherwise it doesn't work. Okay, so that's a mistake there. And then the answer will be C. Okay? So you just divide by 2 because this is the F is 2x, and so it's going to be half of that. Yeah. Which of the following forms a saturated solution when we have 0.1 moles in 1 liter? If we have 0.1 moles in 1 liter and it is unsaturated, what kind of a compound would that be? Soluble or low solubility? That would be soluble. So we need something that is low solubility, yes, to make it form a saturated solution, so it's not able to dissolve the entire 0.1 moles in 1 liter. Now, there actually is a problem with this question, I think. I think there's a problem with some answers. For one thing, Ca2SO4 is not a compound. Yes? Like, that's just not a thing. If we were, and I think there might be, let's check the answers because I think there might be problems with the other answers. So magnesium sulfite is low solubility and magnesium sulfate is high solubility. You know what I'm going to guess? I'm going to guess that this is a typo and that this should be Na2SO4, because then this would be soluble, this would be soluble. MgSO4 is soluble. The only one then that is low solubility is that one. So the question has a problem. It should be Na2SO4, and then your answer should be C. So a saturated solution is not able to dissolve 0.1 moles in 1 liter. And that is low solubility. So B should be Na2SO4, not Ca2SO4. That makes a lot more sense. That's why the 2 is there. 69, which of the following has the highest solubility? What do you guys think? Do you see anything immediately there that jumps out as being very soluble? Yes? NO3, yeah, because NO3 is soluble with everything, and so it's going to, anything that's, if you have a list of a bunch of things and you're like, well, this one's completely soluble, you can't be more soluble than completely soluble, right? So that's going to be this one. Which of the following has the lowest solubility? Well, acetates are all soluble, yes. We don't talk about them a lot, but they are all soluble. Nitrates are all soluble. So we're down to 2. And you can check that out on your data booklet if you want to. But you can also remember that most chlorides are soluble. There's only a very few things that chlorides are low solubility with, whereas carbonate down at the bottom of the table is low solubility with most stuff. Yes? So carbonate is going to be the least soluble. So calcium carbonate is the lowest solubility. Which of the following can be used to prepare a 0.1 molar solution. What's magic about 0.1? Soluble. So let's go to our solubility table. We have, I mean, I know that phosphate's right down at the bottom, so it's not soluble with hardly anything, so that's not going to be it. How about silver bromide? Do you know that one? No? Okay, let's look up silver with bromide. It's not soluble, okay? Silver and bromide are not soluble. So not that one. Now we have a choice between barium sulfate and strontium hydroxide. Sulfate is barium sulfate, that's low solubility. And strontium hydroxide is actually, it's the one of the alkaline earths that is actually soluble with hydroxide, at least on this solubility table. Alkaline earth. So it's going to be this one, because that's the only one that's soluble. (72). Which of the following will have the lowest carbonate concentration? Which one can we get rid of immediately? Because that's completely soluble, so it's not going to have the lowest concentration. So now we need to decide between magnesium, calcium, and strontium. If we go to page 4, magnesium, calcium, and strontium are all down here, so that does us no help, yes? Where would we need to go next? Our KSP. So we're going to be looking for the one with the smallest KSP. So carbonates. Magnesium carbonate is 10 to the minus 6. That's magnesium. Strontium carbonate is 10 to the negative 10. So if we were just looking at strontium and magnesium, which one would have the lower carbonate concentration? The strontium, and then we'll just do a quick check on calcium, which is way up here, and calcium is 10 to the negative 9, so it would also be higher than the strontium, so it's going to be strontium carbonate. (73). This is a bad question. We're just going to omit 73 because lead fluoride is not on our table. So just cross out number 73 because it's a bad question. And you're like, it's not here. It's not here. How am I supposed to do this? Yeah, it's a bad question. Okay. 77. The solubility of barium chromate is 1.1 times 10 to the minus 5. What is the value of KSP? Once again, this is where you could, because it's multiple choice, use the shortcut. We have an AB type compound. It's 1 ion to 1 ion. Yes? 1 barium for 1 chromate. So what's the expression for KSP? KSP is equal to x squared. Okay? And x is the solubility, so we're going to take 1.1 times 10 to the minus 5 and plug it in there. So KSP is equal to 1.1 times 10 to the minus 5, and we're going to square that. And we get 1.21 times 10 to the negative 10. (78). The KSP for cadmium carbonate. Oh, this is like the reverse of the last one, because this time we have the KSP, which is 1 times 10 to the negative 12. And this is also a 1 to 1 ion ratio. So KSP then is equal to x squared, and x is the solubility. And so the solubility then is equal to the square root of 1 times 10 to the minus 12, which is 1 times 10 to the negative 6. Oh, that is an, oh, no, no. Grams per liter. Grams per liter. Oh, nasty. Because I would have looked at that and gone, hey, I got 1 times 10 to the negative 6. So now you would have to convert, this is moles per liter. And we would have to convert that into grams per liter. So we need to cancel our moles. Cadmium, what's the molar mass of cadmium? Plus 16 times 3, 172.4. Yes? Well, that's just wrong. So let's see what we actually get here. Times 1e6 negative equals 1.7 times 10 to the negative 4. It should be D. Okay. That was number 78. Now we want number 84. Which of the following would cause solid to dissolve? Oh, this one tricky. I can do 85 as well, yeah. It's definitely not CO3, right? Because that would cause it to shift to the left because we've increased concentration of CO3. Oh, look, this one's also CO3. And I don't know why magnesium, oh, magnesium? You know what, like HCl will work. I don't know why magnesium nitrate is here, that makes me sad. Because two H's get together with CO3 2 minus and make H2CO3, which then breaks down into CO2 and H2O, which is kind of a trivial little point that you probably won't be tested on, but if you know it, like it's kind of like a bonus. I don't know. Anyway, but I don't know why MgNO3 is there. That makes me sad. It shouldn't be there. It could possibly be another correct response. The answer key is wrong? Okay. It said B? Well, B is just definitely wrong. I would have too, but that gives us 2 answers. And that's no good, so I need to fix this. This last part, yes, there definitely is. Number 90, I would like you to just cross out number 90, number 90. It's just wrong. There's no correct answer, as far as I can tell. Okay, let's take a look at this one. We have sodium oxalate is added. So that increases our concentration of oxalate. The system shifts to the left. So we're either looking at A or B. And what happens to the solubility of the lead oxalate? It decreases. And like I said, number 90 is just wrong. This? Well, no, because this, I mean, none of these answers are correct. None of them. Okay, they're just wrong. Yeah, we could look at 91. Let's take a look at 91. So we add some solid KBr to a saturated solution of AgBr. So what have we done if we add solid KBr? We've increased Ag, decreased Ag. We increased the concentration of Br, yes? By adding KBr, because it dissociates into K plus and Br minus. So it's now going to shift to the left. So let's graph our concentrations here. I'm just going to arbitrarily put Ag here, and I'll put Br here. Okay. Our Br concentration increased. What will happen to its concentration now? What would the graph look like? It'll go down. Where will it get to? Somewhere above its original value. It doesn't really matter where. Okay, somewhere above its original value. And what will happen to silver? It will also go down. So what can you say about the concentration of silver after equilibrium is reestablished? Silver has decreased, so we're either looking at this one or this one. What has happened to our bromide? It has increased, right, because it's bigger than it was originally. So we're looking at B. Anything else we'd like to look at? Okay. You have a choice. We can start acids and bases today, or I can just start it tomorrow. Start it tomorrow? Okay. So you can do a little more work on your review. The answer key for the written response you just got. Yes. Yes. Of course. Yes.